Greetings! Welcome to my channel, Human, Evidently, where I provide evidence-based videos on human origins, paleoanthropology, archaeology, and evolutionary science for adults.
Photogrammetry for Archaeology, a cross-paper comparison of the use of UAV in archaeological and anthropological contexts. Today we're covering UAV photogrammetry for archaeology and CRM, something a little different from our usual subject matter. This video presentation is meant to build on your knowledge from reading the studies cited in the description below. If you have not already, I strongly suggest you pause the video and get access to these papers. While you can watch the video before or while reading the studies, you might not get as much from this presentation as someone who has already familiarized themselves with the source material. That said, there are some solid critical thinking components to this presentation that may impact your reading of the material in a very useful way. With that, let's begin. UAV photogrammetry has become a prominent method in archaeological and cultural heritage research, but its value depends on how carefully the method is matched to the research question. Across these 4 studies, drones are presented as flexible tools for low-altitude imaging, 3-dimensional documentation, landscape survey, site monitoring, and heritage conservation. Campana situates UAVs within the longer history of archaeological aerial photography, showing how drones improve positional control, planned coverage, and site scale or landscape scale recording when compared with earlier low-altitude platforms. Themistokleous emphasizes their usefulness for cultural heritage documentation, especially when UAV imagery is processed through photogrammetric workflows to create orthomosaics, point clouds, digital surface models, and 3D reconstructions. At the same time, Field, Waite, and Wandsnider demonstrate that UAVs cannot be assumed to replace pedestrian survey, particularly when the task involves detecting small artifacts in vegetation or visually complex ground conditions. Pecci adds a methodological caution. Drone survey results depend not only on equipment and software, but also on archaeological context, site preservation, ground control, workflow design, and interpretive expertise. Together, these papers show that UAV photogrammetry is a powerful archaeological method when used critically, but a limited one when treated as a universal solution. Campana's review begins from a methodological premise. Drone archaeology belongs to a longer history of low-altitude archaeological recording. The paper examines unmanned aerial vehicles as part of an expanding remote sensing toolkit, with attention to excavation recording, architectural documentation, site survey, landscape survey, exploratory prospection, woodland archaeology, and diagnostic imaging. The central claim is neither technological celebration nor rejection. UVs change the scale, resolution, repeatability, and interpretive range of archaeological observation, while still requiring careful attention to research design, platform choice, sensors, processing workflow, and interpretation. Campana, 2017. Campana's core argument is that UAVs have become archaeologically significant through the convergence of platform mobility, sensor development, and photogrammetric processing. Traditional low-altitude platforms could produce useful images, but they often lacked reliable positional control and planned coverage. UAVs extend archaeological recording by allowing repeatable survey patterns, controlled overlap, and movement across excavation, monument, site, and landscape scales. The argument here is that drones transform archaeological perception. They influence what can be documented, what can be modeled, and what can be interpreted from spatial evidence. The historical background is essential to Campana's argument. Close-range aerial photography did not begin with drones. Archaeologists used balloons, kites, masts, poles, booms, towers, blimps, and helikites long before commercial UAVs became widely accessible. Campana identifies Giacomo Boni's balloon photography over the Roman Forum in 1900 as an early archaeological use of low-altitude aerial recording. This history places UAVs within a technical lineage rather than treating them as an isolated innovation. The continuity also clarifies the methodological problem. Aerial perspective has long been useful, but controlled, repeatable, high-resolution coverage remained difficult with older platforms. Campana, 2017. Key terms. UAV refers to the unmanned aerial vehicle, while UAS is more precise when the entire system is meant. Aircraft, sensors, ground control, operator interface, positioning technology, and processing pipeline. RPAS, RPV, SUAV, and MAV are related terms that specify remotely piloted systems, or smaller vehicle classes. Campana also distinguishes image-based modeling, or multi-image photogrammetry, from simple photography. A photograph records a view. Photogrammetric modeling uses overlapping images to generate spatial products such as point clouds, meshes, orthophotos, digital surface models, and three-dimensional documentation. UAV platforms. Fixed-wing UVs are suited to landscape-scale coverage. They can survey larger areas with efficient flight paths, although they have limited ability to hover or record vertical structures closely. Multi-rotor UVs are better suited to excavations, monuments, walls, facades, and small area documentation, since they can hover, acquire oblique imagery, and maneuver around complex architectural forms. Campana's point is complementarity. Platform choice follows research scale, required resolution, payload, wind conditions, flight time, and the spatial form of the archaeological target. Campana identifies several core archaeological applications: three-dimensional documentation of excavations, three-dimensional survey of monuments and historic buildings, survey of archaeological sites and landscapes, exploratory aerial survey, woodland archaeology, and diagnostic or heritage monitoring work. These applications share a reliance on vector-based and raster-based outputs. Point clouds, meshes, digital surface models, orthophotos, contour maps, and georeferenced models allow archaeological information to move from image capture into measurable spatial analysis. UAVs are therefore best understood as survey systems, linking platform, sensor, flight planning, ground control, processing, and archaeological interpretation. The major advantage Campana assigns to UAVs is controlled mobility. Compared with kites, balloons, and helikites, UAVs provide better positional control, more predictable image overlap, and better compatibility with planned photogrammetric coverage. These qualities support technical documentation rather than only visual illustration. UAVs also permit flexible survey at multiple scales, from exposed excavation surfaces to buildings, monuments, fields, and wider archaeological landscapes. The methodological gain comes from repeatable, high-resolution recording that can be processed into spatial datasets suitable for analysis, conservation, and long-term comparison. UVs require investment, training, regulatory awareness, battery management, sensor selection, ground control, and substantial processing time. They are not automatically superior to masts, kites, or balloons when the goal is a simple illustrative image. Interpretation remains a separate archaeological task. A high-resolution orthophoto can still produce weak archaeological conclusions when the survey design is poor, the sensor is unsuitable, or the analyst lacks contextual knowledge. Campana's caution is that UVs increase archaeological capacity, but they do not remove the need for method, expertise, and critical interpretation. Let's test our understanding. First, what is Campana's thesis? I'll give you 5 seconds to pause this video presentation and decide on your answer. Campana's thesis is that UAVs expand archaeological remote sensing by improving controlled, low-altitude, high-resolution documentation across multiple scales. Second, why might UAS be the more accurate term? I'll give you 5 seconds to pause this video presentation and decide on your answer. UAS might be the more accurate term because it refers to the entire operational system rather than only the vehicle. Third, how do UAVs improve on kites, balloons, and helikites? I'll give you 5 seconds to pause this video presentation and decide on your answer. UAVs improve on these other platforms because they improve positional control, flight planning, overlap, and repeatability. Fourth, when are drones not the best option? I'll give you 5 seconds to pause this video presentation and decide on your answer. The answer is that simple illustrative photography may be handled more efficiently with a cheaper, simpler platform, Campana 2017. Campana's contribution is a disciplined, state-of-the-field synthesis. The paper shows that drones are useful for archaeological documentation, diagnostics, and survey, while also insisting that technology does not interpret archaeological evidence on its own. UAVs alter archaeological practice by changing the resolution, frequency, and spatial reach of observation. Their most beneficial use emerges when the research question, platform, sensor, flight plan, ground control, processing method, and interpretive framework are aligned. Field, Waite, and Wandsnider, 2017. Field, Waite, and Wandsnider shift the discussion from broad potential to empirical testing. Their study asks whether an accessible, lower-cost drone can assist or replace pedestrian surface survey for small artifacts in a grassland setting. The paper's value lies in its practical realism. The authors do not test an ideal laboratory system or high-end sensor package. They test an out-of-the-box DJI Phantom 4, the kind of platform that many archaeologists, agencies, and field schools might realistically consider. UAVs may improve archaeological efficiency, but their effectiveness must be evaluated against specific survey targets and environmental conditions. In Nebraska, archaeological work is constrained by private land access, limited field time, growing seasons, weather, and the large amount of unsurveyed land. Drone-sourced orthoimagery seems promising under those conditions. The study tests a practical question. Can affordable UAV imagery identify small surface artifacts in moderate grassland vegetation at a level that would make it useful for archaeological survey? The study design compares pedestrian survey with drone-sourced orthoimage survey. The survey area measured roughly 190 by 150 meters and included variation in grass height, brush, relief, and ground visibility. The authors seeded 40 artifacts using 3-centimeter washers painted black and white, arranged in high-density and low-density distributions. 3 undergraduate surveyors with field school experience conducted pedestrian survey at 10-meter intervals, then evaluated the orthoimage separately. The control design allowed the authors to compare detection success across 2 survey methods, while holding the study area, participant group, artifact number, and artifact density constant. The results were strongly negative for small artifact detection through the drone-sourced orthoimage. In pedestrian survey, 11 of the 40 seeded artifacts were located. In the orthoimage survey, participants placed 13 possible artifact points, but none corresponded to actual artifacts. The authors could identify only 2 artifacts after overlaying known GPS locations, and those would not have been recognized confidently without the seeded location data. The failure reflects limits in resolution, vegetation visibility, background texture, object contrast, and false positive recognition. White objects drew more attention than black objects, suggesting that contrast affected perception more than archaeological signal. The authors argue that drone-based surface survey needs a more precise model of detectability. Artifact recognition depends on more than pixel size. It also depends on object length, width, color hue, color intensity, vegetation, background texture, lighting, and the analyst's visual search process. The paper invokes the need for a four-dimensional extension of Nyquist-Shannon logic, linking image resolution to artifact size and contrast. False positives receive special attention, since a method that produces too many false targets can lose any efficiency gained through remote inspection. Let's test our understanding. First question, what was the main finding of this paper? I'll give you 5 seconds to pause this video presentation and decide on your answer. The main finding is that the low-cost UAV method did not successfully identify small seeded artifacts under the tested grassland conditions. Second question, why is this paper important methodologically speaking? I'll give you 5 seconds to pause this video presentation and decide on your answer. The paper is methodologically important since it tests a common use scenario, rather than assuming drone utility from best-case examples. Third question, what variables affected artifact visibility? I'll give you 5 seconds to pause this video presentation and decide on your answer. The major variables affecting visibility were artifact size, color contrast, vegetation, surface texture, image resolution, sensor quality, and processing workflow. Final question for this section. Does the paper argue that drones are useless for archaeology? I'll give you 5 seconds to pause this video presentation and decide on your answer. No, the authors do not argue that drones are useless in archaeology. They argue that drone utility is conditional, especially when the target is small, low contrast, or partially obscured. Field, Waite, and Wandsnider's study shows that UAV efficiency depends on artifact size, surface visibility, vegetation, sensor resolution, processing choices, and false positive rates. The DJI Phantom 4 produced useful geotagged imagery and efficient field coverage, but it did not provide reliable small artifact detection in moderate vegetation. The study's conclusion is this: out-of-the-box drones may support mapping, feature documentation, macro-scale artifact recording, and field logistics, but they should not replace pedestrian surface survey without context-specific validation. Themistokleous, 2020. Themistokleous approaches UVs from cultural heritage documentation and monitoring. The chapter focuses on archaeological and cultural heritage sites in Cyprus, using UAV imagery and photogrammetry to generate orthophotos, digital surface models, three-dimensional models, and documentation products. Its emphasis differs from Field, Waite, and Wandsnider's surface artifact experiment. Here, the central concern is documentation of sites, structures, and cultural landscapes, especially when non-invasive, high-resolution, repeatable recording is needed. UVs provide an affordable, efficient, non-invasive method for documenting and monitoring cultural heritage sites. High-resolution aerial imagery can be processed through photogrammetry to create ortho images, point clouds, digital models, and textured three-dimensional reconstructions. Themistokleous highlights case studies in Cyprus to demonstrate how UAV workflows can document architectural heritage, archaeological sites, and surrounding cultural landscapes. The emphasis is on record creation, monitoring, conservation, and communication, rather than small object discovery. Themistokleous identifies several advantages: low cost compared with many traditional documentation methods, non-contact data collection, access to areas that may be dangerous or difficult to enter, high spatial resolution, repeatable monitoring over time, and the ability to include the surrounding cultural landscape. UAVs also support rapid production of three-dimensional digital models. These advantages are best exploited when the archaeological target is a structure, visible site, standing architecture, or monitored landscape, rather than a small artifact hidden in vegetation. Themistokleous, 2020. The chapter distinguishes between copters and gliders, and between different sensor types. Copters provide stability, maneuverability, hovering, oblique imaging, and controlled photography, but they are limited by battery life and require calibration and skilled operation. Gliders can cover larger areas and fly longer, but they require more training and operational support. Sensors may include visible spectrum cameras, multispectral cameras, infrared cameras, and thermal cameras. This distinction is methodologically important. A UAV is a platform, while archaeological information depends on the sensor, flight plan, processing workflow, and research question. The photogrammetry workflow begins with high-resolution aerial images from UAVs. Those images are processed with structure from motion software to align photographs, estimate camera positions, and generate a sparse point cloud. Multi-view stereo procedures then create a dense point cloud, which can be used to generate a digital surface model, orthomosaic, digital terrain model, contour map, mesh, or textured three-dimensional reconstruction. Ground control points allow the model to be scaled and georeferenced accurately. The resulting products can support documentation, monitoring, analysis, conservation planning, and presentation. Important technical concepts. Photogrammetry is the measurement of three-dimensional coordinates from overlapping photographs. Aerial triangulation uses images taken from different locations to reconstruct object points. Structure from motion estimates camera positions and scene geometry from overlapping imagery. Sparse point clouds represent initial matched features. Dense point clouds provide fuller geometric reconstruction. Orthophotos are corrected image mosaics. Digital surface models include visible surface features. Digital terrain models represent terrain. Building information modeling extends documentation by integrating geometry, plans, elevations, sections, and attribute information. Let's test your knowledge. First, what is the central claim of Themistokleous' chapter? I'll give you 5 seconds to pause this video presentation and decide on your answer. The central claim is that UAVs are effective tools for non-invasive cultural heritage documentation and monitoring. Second, how does Themistokleous connect UAVs to photogrammetry? I'll give you 5 seconds to pause this video presentation and decide on your answer. The chapter connects UAVs to photogrammetry through overlapping aerial images, which become point clouds, orthophotos, digital models, and textured reconstructions. Third, why are GCPs important? I'll give you 5 seconds to pause this video presentation and decide on your answer. GCPs, or ground control points, are necessary for scale, georeferencing, and spatial accuracy. Finally, how does BIM extend UAV documentation? I'll give you 5 seconds to pause this video presentation and decide on your answer. Building information modeling extends UAV documentation by converting point clouds and three-dimensional models into structured plans, sections, elevations, and conservation-relevant documentation. Themistokleous presents UAVs as integrated documentation systems. Their main value lies in producing high-resolution, repeatable, non-invasive records of cultural heritage places. Case studies in Cyprus show how UAV imagery can be transformed into point clouds, three-dimensional meshes, orthophotos, digital elevation products, BIM models, and even printed models. The chapter's conclusion is that UAVs are most useful when image capture, ground control, photogrammetric processing, and conservation goals are designed as a single workflow. Pecci, 2020. Pecci's article brings the discussion back to method, archaeological context, and interpretive caution. The paper addresses the widespread use of drones in archaeology and argues that apparent ease of use has sometimes encouraged weak workflows and overconfident conclusions. Pecci is especially concerned with ruined archaeological areas, where drone imagery and photogrammetric models can be valuable, but only when the researcher understands the limits of the equipment, the territorial context, and the variables that shape archaeological visibility. Drone survey success depends on more than platform performance or software output. Aerial images and three-dimensional models can improve archaeological documentation, but their quality depends on survey planning, sensor type, light conditions, land morphology, ground control, processing method, data management, and the analyst's interpretive skill. Pecci warns against a mechanical view of photogrammetry, in which software-generated models are treated as automatically reliable. Archaeological interpretation must remain grounded in site formation, landscape history, and the limits of visibility. The increasing accessibility of UAVs and structure from motion software has encouraged rapid adoption, but not always careful practice. Weaknesses may appear in accuracy assessment, data acquisition, processing, data management, or interpretation. Pecci also notes the absence of a general archaeological manual for UAV use. Under those conditions, technical mistakes can become archaeological mistakes, especially when imagery is used to guide conservation, restoration, or interpretation of damaged sites. Pecci outlines a full workflow. The first step is defining the study area, boundaries, obstacles, morphology, and known or suspected archaeological points of interest. GIS tools such as QGIS or Google Earth can assist planning. The second step is technical preparation, including batteries, GPS connection, takeoff, flight, and landing. Image acquisition should include zenithal and oblique photographs, with altitude and perspective selected according to the camera, desired detail, and research objective. Ground control points should be recorded by GPS or total station. Blurred, redundant, and takeoff or landing images should be removed before processing. Structure from motion software can then produce point clouds, meshes, textured models, orthophotos, DEMS, and georeferenced outputs. The archaeological territorial context is Pecci's most important concept. It refers to the landscape setting in which a site or evidence of past land use exists, shaped by human and natural processes. Urbanization, agriculture, erosion, landslides, fires, floods, abandonment, spoliation, reuse, and the passage of time all influence what remains visible from above. Pecci contrasts the Roman villa of San Giovanni at Ruoti, difficult to interpret from drone imagery due to long-term spoliation and modern agriculture, with the castle of Lauria, easier to read from above due to better preservation. Pecci summarizes the major variables as equipment quality, equipment type, survey method, processing method, acquisition period, data management, and interpretive experience. These variables are linked to archaeological context. Light conditions, vegetation, land morphology, sensor quality, computing capacity, and data handling can shape the final model. The point is methodological discipline. Drone survey success depends as much on archaeological judgment and workflow control as on the drone. Software can generate a model, but it cannot independently determine what the model means archaeologically. Let's test your understanding. First question, what is Pecci's main warning? I'll give you 5 seconds to pause this video presentation and decide on your answer. Pecci's main warning is that easy drone operation and accessible photogrammetry can encourage poorly controlled methods. Second question, what does territorial archaeological context mean? I'll give you 5 seconds to pause this video presentation and decide on your answer. Territorial archaeological context means the historical and environmental landscape conditions that shape what remains visible, preserved, buried, reused, or erased. Third question, why might one site be easier to read from UAV imagery than another site? I'll give you 5 seconds to pause this video presentation and decide on your answer. One site may be easier to read from UAV imagery when elevations, ditches, terraces, or architectural forms remain visible, while another may be obscured by spoliation, agriculture, erosion, or poor preservation. Fourth question, what does Pecci recommend for the future? I'll give you 5 seconds to pause this video presentation and decide on your answer. Pecci recommends stricter and more clear methodological standards, including a manual for archaeological UAV survey, processing, data management, and interpretation. Drones and photogrammetry can substantially improve archaeological documentation, but their value is conditional. The researcher must understand acquisition, processing, georeferencing, data management, and interpretation. Poorly planned UAV work may produce visually impressive models with weak archaeological reliability. Pecci's contribution is therefore a critique of technological overconfidence. Ultimately, drone survey must be evaluated through archaeological context, preservation, landscape history, sensor choice, processing decisions, and the expertise of the analyst. Cross-paper comparison. The 4 papers form a useful comparative sequence. Campana provides the broad state of the field. Field, Waite, and Wandsnider provide an empirical limit case. Themistokleous emphasizes cultural heritage documentation and monitoring. Pecci provides a methodological critique focused on territorial context and workflow variables. Together, they show that UAV archaeology cannot be evaluated through a single standard of success. Detection, documentation, monitoring, modeling, mapping, conservation, and public visualization each require different methods and different expectations. The shared theme is that all 4 papers treat UAVs as powerful archaeological tools when combined with photogrammetry, georeferencing, and 3-dimensional modeling. Campana emphasizes the expansion of low-altitude remote sensing. Field, Waite, and Wandsnider evaluate whether that expansion can apply to small surface artifact detection. Themistokleous shows how UAV workflows support cultural heritage documentation. Pecci stresses that contextual and methodological variables determine whether outputs are archaeologically meaningful. The common ground is conditional utility. Drones become useful when method, context, and research goal align. The major differences are methodological. Campana asks what drones can do for archaeology as a developing remote sensing field. Field, Waite, and Wandsnider ask whether low-cost drone imagery can detect small artifacts in a real-world grassland setting. Pecci asks which variables and contextual factors affect survey success. Themistokleous asks how UAVs can support high-resolution documentation, monitoring, BIM, and heritage conservation. The different conclusions reflect different research goals. A drone may fail as a small artifact detection system while still succeeding as a documentation platform for visible architecture or cultural landscapes. Campana is a review paper focused on the state of UAV archaeology. Field, Waite, and Wandsnider conduct an experiment on drone-sourced ortho images and surface artifact detection. Pecci offers a methodological critique centered on context, variables, and interpretive standards. Themistokleous presents review and case study evidence for cultural heritage documentation and monitoring. So, it follows that UAVs are neither universally transformative nor methodologically trivial. Their value depends on what archaeologists ask them to do. UAVs cannot universally replace traditional archaeological survey. They are valuable for documentation, mapping, modeling, and monitoring, but territorial context, preservation, workflow, and expertise shape whether drone outputs or their interpretations can be considered reliable. Added to that, low-cost UAV imagery may fail for small artifact detection in moderate vegetation and may generate false positives. Ultimately, the conclusion is that UAVs are complementary tools, especially great for documentation and spatial modeling within certain limitations. And they are also not automatic substitutes for pedestrian survey. It's important to remember to avoid technological determinism. UAVs are effective for some archaeological tasks and weak for others. They can document standing structures, excavations, visible features, cultural landscapes, and monitored heritage sites with high spatial resolution. They can also fail when the target is small, obscured, low contrast, or embedded in complex vegetation. The key variables are research question, artifact or feature size, site visibility, preservation, sensor quality, flight planning, image resolution, ground control, processing workflow, and analyst expertise. UAVs extend archaeological survey. They do not eliminate the need for field verification. The collective takeaway is that drones are tools of conditional archaeological value. They are not inherently good or bad. Their value depends on the archaeological question, site visibility, preservation, sensor quality, image resolution, flight planning, ground control, processing workflow, vegetation, artifact size, and interpretive expertise. Across the 4 papers, evidence of the most valuable uses points at our documentation, mapping, monitoring, 3-dimensional modeling, and cultural heritage conservation as the prime goals when choosing to use a UAV or UAS. The weakest tested use is small surface artifact detection in moderate vegetation using an out-of-the-box drone. A responsible archaeological workflow treats UAVs as part of a broader evidentiary system, integrated with field survey, ground control, contextual analysis, and critical interpretation. Now it's time to figure out just how much you know with some short essay questions. Your response should draw connections across multiple papers, use specific examples from the presentation, and evaluate both the strengths and limits of UAV photogrammetry as an archaeological method. 1. Method selection and research design. Imagine that an archaeological team has limited funding and access to a privately owned landscape for only 3 days. The team wants to identify possible archaeological features, document visible remains, and decide where future pedestrian survey should be concentrated. How should the team decide whether UAV photogrammetry is an appropriate method? In your answer, discuss research goals, scale, visibility, equipment limits, ground control, and the relationship between aerial and pedestrian survey. 2. Accuracy, visibility, and interpretation. UAV imagery can produce visually persuasive orthomosaics and 3D models, but visual clarity does not automatically equal archaeological accuracy. Explain how vegetation, surface contrast, artifact size, preservation, site formation processes, and post-abandonment land use can affect what archaeologists think they see in drone-derived data. How should researchers guard against over-interpreting aerial imagery? 3. Comparing documentation and detection. Several of the papers show UAVs performing well for documentation, modeling, monitoring, and mapping, while field et al. Show limits in detecting small surface artifacts. Why might UAV photogrammetry be used for a documentation tool instead of as a small artifact detection tool? In your answer, compare the evidentiary demands of recording architecture or landscape features with the demands of identifying small artifacts in mixed ground cover. 4. Technology and archaeological expertise. Pecci warns that the apparent ease of drone operation and photogrammetric software can encourage weak methodology. Evaluate this concern. What kinds of technical knowledge and archaeological judgment are needed before, during, and after UAV data collection? Discuss flight planning, image overlap, sensor choice, georeferencing, data processing, and interpretation. 5. Synthesis and future application. Based on the 4 papers, propose 1 responsible future use of UAV photogrammetry in archaeology or cultural heritage work. Your answer should identify a specific research or preservation problem, explain why UAV photogrammetry would be useful, identify at least 2 limitations or risks, and describe how the project design would reduce those risks. UAV photogrammetry is a useful, albeit conditional method of archaeological survey. Drones can expand what archaeologists are able to document, especially at low altitude and high spatial resolution, and they can produce durable visual records of excavations, monuments, landscapes, and cultural heritage sites. However, the same technology can also produce misleading confidence when image quality, visibility, artifact size, ground cover, georeferencing, or post-processing limitations are not evaluated carefully. Field, Waite, and Wandsnider's results are especially useful as a corrective to technological optimism, since their study shows that a low-cost UAV workflow failed at the specific task of identifying small surface artifacts in moderate vegetation. Pecci's emphasis on territorial archaeological context further reinforces the need to interpret UAV data through site formation history, preservation conditions, land use, and methodological control. The most beneficial use of UAV photogrammetry, then, is as part of an integrated archaeological workflow that combines aerial documentation, ground observation, spatial control, technical skill, and critical interpretation. Special thanks to my Patreon subscribers: Red Fox the Starfish, Nori the Salty Cat, and Gary, Jack, and Mark the Porpoises. The value of your kind support is immeasurable. Thanks for spending this time with me on Human, Evidently. I hope you're leaving with a clearer understanding of the subject and a deeper curiosity about the story of life, evolution, and our place within it. Until next time, keep asking those good questions. If you want to support my channel, please consider subscribing here and on Patreon, where you can access my content for free or contribute a small donation to get your name at the end of my videos. I'm working on a series of educational material for middle grade readers and 2 science fiction novels. Such endeavors are only made possible by contributions from viewers like you.